Good morning, everyone, and welcome to the final session of Specialist Mathematics Revisions. Today we're doing Graph Sketching Part 2, and my name is Stephen Crouch from Frankston High School. So in today's session, we'll be looking at reciprocal functions as well as their graphs. We're going to look at rational functions and their graphs. We're going to look at how to apply calculus to reciprocal and rational functions along with their graphs. And finally, we're going to look at strategies for using our CAS to solve exam-style questions. Okay, so the first one we're doing is reciprocal functions and graphs. So reciprocal functions typically have the form 1 over fx, but we can, of course, just multiply it by constant k, and we get k over fx. The main feature that reciprocal functions have is that we get vertical asymptotes of reciprocal functions when the denominator has a root. In other words, the denominator is equal to 0 at a particular x value, and that will lead to a vertical asymptote on the reciprocal function graph. Another point to note is that when your x values approach positive or negative infinity, your reciprocal function, or your reciprocal graph rather, will approach 0. In other words, it will approach the x-axis. Okay, so let's look at an example of what I mean by all those theories there. So what I've got is a basic parabola here. I've called it FB for F blue of x. Let's talk about a couple of features that we've got here. I've got x equals 1 and x equals 3 are two x-intercepts or roots of the parabola. I've got a y-intercept at x at y equals 3 as well. Okay, so what does the reciprocal graph look like? It looks like this. It kind of looks like a displaced truncus with an upside down parabola as well over there. So why does the graph look like this, and where are all the main features? Okay, so let's look at the first feature. This blue point here, as I said before, is one of the roots of the parabola. Because it's a root of the parabola, it leads to a vertical asymptote of the reciprocal graph. Moving on to the next one, again, I've got x equals 3, which is a root of the parabola, which also gives a vertical asymptote of the reciprocal. Furthermore, I've got a horizontal asymptote over here, which is y equals 0. Okay, so I've got the equation of the graph we have here is FR, which is F red, is 1 over FB of x. So in other words, the red graph is the reciprocal of the blue graph. And finally, let's look at the y-intercept. So the y-intercept of the parabola is 3. So of course, the reciprocal of that is 1/3, which is the y-intercept of the reciprocal graph. Okay, so we're going to go through a couple more examples showcasing how these features play out when we take reciprocals. So let's look at the green graph. It is a cubic with equation y equals x minus 1, x minus 3 squared. So that is basically a regular x-intercept at x equals 1 and a repeated root or a turning point on the x-intercept at x equals 3. Okay, so the x-intercepts, which are 1 and 3, of course, as we said before, lead to vertical asymptotes on the reciprocal. So my vertical asymptote here at x equals 1 is a result of the root at x equals 1 on the cubic. Likewise, the vertical asymptote at x equals 3 is a result of the repeated root at x equals 3 on the cubic. Now, what I do want to make a very important point about is the way the reciprocal graph behaves and approaches the asymptote depending on the way the x-intercepts look. So if you look at x equals 1, this is an x-intercept where it goes from negative y values up to positive y values. And that's why on the reciprocal graph, the same thing is happening as well. As you approach x equals 1 from the negative side, what happens is the y values of the reciprocal approach negative infinity. And as you approach x equals 1 from the positive side, the y values of the reciprocal approach positive infinity. So that sort of behavior is what is normally in conjunction with what it looks like for a rectangular hyperbola. Whereas if you look at what's happening at x equals 3, because the y values on either side of the x equals 3 root are both positive, what ends up happening is that the behavior of the reciprocal graph is it approaches positive infinity as you approach x equals 3 from both sides. So that is the sort of behavior you'd expect from a graph of a truncus. So as you can see, we still get asymptotes at roots of the original graph. However, the behavior differs quite remarkably. The final thing I do want to talk about is the turning point, or the local maximum on the cubic. So around here, I've got a local maximum on the cubic, which corresponds to a local minimum on the reciprocal. So at the exact same x value, a local minimum occurs on the reciprocal graph, which corresponds to a local maximum on the original cubic graph. And finally, we also have our horizontal asymptote, which is y equals 0. And as you can see, the graph approaches it as x approaches positive and negative infinity. Okay, let's move on to the next one. So this time, I've got a bell curve over here, which has a turning point at 1, 2, and that's your f sine graph. And I've also got an f Brown graph. So what might be different here is that my original graph, my bell curve, has a horizontal asymptote at y equals 0, and I'm taking the reciprocal of that. And what you might notice is that the way that the two graphs are related is very much the same as if the brown graph was the original and the blue graph was the reciprocal. So what's different about this graph compared to the other two ones is the distinct lack of vertical asymptotes. We only have a single asymptote here, which is y equals 0. We don't have any vertical asymptotes. And there's a very good reason for that. And that reason is that neither of these graphs have an x-intercept. So as we said before, the reciprocal graph will have a vertical asymptote when the original graph has an x-intercept or a root. Clearly, neither of these two graphs have an x-intercept or a root, and that's why we don't have any vertical asymptotes. So really, the only main feature we've got is that a maximum turning point at 1, 2 has turned into a local minimum turning point at 1, half. Furthermore, as x approaches positive and negative infinity, the sine original graph approaches the asymptote, and the reciprocal graph will go off towards infinity. Okay, so now let's go for our last example over here. I'm taking the reciprocal of the natural log graph. So as you can see, the natural log graph, as we know, it has a vertical asymptote at x equals 0. It has a root or x-intercept at x equals 1, and then it just approaches infinity as you take x towards infinity as well. So what's happening is, if you look to the right of x equals 1, you have this positive part over here, which is what the previous graphs looked like as well. As the original graph rises towards infinity, the reciprocal graph will fall towards the asymptote. Of course, there's a vertical asymptote at x equals 1 due to the x-intercept there. Now, as you go to the left of -1, your reciprocal graph goes towards negative infinity. And as you go towards x equals 0, because the natural logarithm graph goes towards negative infinity, the reciprocal graph will approach 0, which is what you're seeing happen over there. Okay, so here we go. Here is our first example. We simply have to find the equations of the asymptotes of the graph given to us. Okay, so what I'm going to do is I'm going to define this. F of x, control template, define it, and use the fraction template. So 2 over x squared minus 4x minus 5. Enter. There we go. So I've defined my function there. So there's a couple of ways we can get the equations of the asymptotes. Number one is I'm going to use the domain command. So domain, I've pressed the book, which is the catalog, and then domain's already selected there. If it's not selected for you, just press D on your keypad and keep scrolling down until you get to domain. So this, the syntax for domain is simply the function, which is f of x and comma x. Enter, and there we go. So we are told that the domain, or the maximal domain of f of x, is every real value except -1 and 5. So those are the two vertical asymptotes. And another way to do this is to solve for the denominator equals 0. Okay, so to get solve, I'm going to go menu 3, 1 to get solve. And to extract the denominator, I'm going to choose menu, 2 for number, 7 for fraction tools, and 3 for get denominator. So this command will extract the denominator of f of x. So let's go f bracket x, close bracket, close the bracket again. I want to equate that to 0 for x and hit enter. There we go. So when the denominator equals 0, x is equal to -1 or x equals 5. So we have vertical asymptotes at -1 and 5, and we have a horizontal asymptote, as always, at y equals 0. So let's see what this looks like visually. This is, of course, the graph of f of x. So now all I want to do is actually place the asymptotes here. The easiest way to do that is to press Menu, 3 for graph entry edit, and 2 for relation. So I'm going to type in x equals -1, and then press the tab button a couple of times, and then press x, and then type in x equals 5. So I've got my two asymptotes there, but they don't really look that good because they're different colors and they're also not dashed. So how do you change the color? Well, you right-click this on the computer software or control menu on the handheld, and then go color, line color, and I'll change it to the same as the graph, which is blue. And I'll do the same thing for x equals 5. Right-click, color, line color, and make that blue. Okay, so of course the question you might be asking right now is how do you get them dashed? Well, the way to do that is to change the attributes. So I'm going to right-click that, number 3 for attributes, and then go down and then press right a couple of times to get dashed. So that's one of the attributes of that line. Similarly, I'm going to repeat that same procedure, attributes, and then I get that over there. Okay, so of course I've got a little tooltip over here as well that also shows me the asymptotes from left to right. Okay, so that's what the graph looks like with all asymptotes sketched in. Okay, so here's a possible exam question. I've got another reciprocal graph with the rule g of x, and we want two things. We want the maximal or implied domain of g, and we also want to sketch the graph of g, labeling all our axes, intercepts, and stationary points. We want to label them with coordinates, and all asymptotes we want to label with equations. Okay, so let's start by finding the implied domain. So before we do that, we must always get started by defining our function. So g of x is defined as, and here's our function tool, fraction tool, 18 over 9 minus x squared. Okay, and there we go, enter. So to get the asymptotes, I'm going to use the domain command as I did before. So book, domain, and then simply type, I can use var, and you can scroll up. I'll eventually find g of x, or rather it's just easier, just type in g of x as it is, comma x. Okay, so as you can see, we'll have two vertical asymptotes at x equals -3 and x equals 3. Also, we will have a horizontal asymptote at y equals 0. So that's one part of part B done. And the implied domain of G would be, I'll show you how to write this if you were to write this as an answer on an exam or a SAC. You would, I'll just type in a comment, and you would say x is an element of, I'll just find element, it's around here somewhere. There we go, there's element, and then you'd want the real number set. Yes, the real number set is around here, and then except, and then you'd use brackets, -3, comma 3. So that right there would be the maximal or implied domain, and that's how you would write the answer to that particular question. Okay, so we want to sketch the graph of g of x now. Okay, so what I've done is I've already sketched the graph of, I'll just get rid of that so we can go through the proper steps right now. Okay, so I'm going to go to menu, graph entry, and function, and simply type in g, open bracket, x, and close bracket. There we go. So here is our g of x function. First thing I'm going to do is I'm going to draw the asymptotes in. So menu, 3, and then 2 for relation, x equals -3. So that is my first asymptote. I'm going to change that attribute to make it look dashed. There we go. Luckily for us, it's already orange. How awesome was that? I'm going to press tab now to go to the next relation, x equals +3. Okay, unfortunately this time it's brown. I'll just change that over to orange. Here we go. And then change the attributes, of course, to make it dashed. There we go. Okay, so we've now got our two vertical asymptotes. Let's draw a horizontal asymptote. We're going to press tab again, and y equals 0 is, of course, the horizontal asymptote. Again, let's change the color for that to make it orange, and I'll change the attributes of it to make it dashed. All right, so I've got y equals 0 over there. Cool, so we've got all these different features there. The only last one we need to do is label the stationary point. So before I do that, I'm just going to find it using calculus. So the best way to do this, this is a really nice little feature of the calculator. I'm going to do menu 371 to solve a system of equations. I want to solve two equations for x and y. Okay, so the first equation we want is, of course, to solve the first derivative equals 0. So shift minus is the shortcut for first derivative, and then press X, press tab, and then type in g of x. Okay, so that's the derivative, and I want to equate that to 0. Next thing I want to do is basically ask it for y equals g of x. So the way I've set this up, it's in such a way that we're going to get an output in the form of a coordinate, or at least an ordered form of x and y. Okay, hit enter, and there we go, x equals 0 and y equals 2. So that tells us that the y-intercept of our graph is basically the stationary point. Okay, so as you can see, we do have a local minimum stationary point at that point over there. So how are we going to show it on the graph? Well, simply go menu, 5 for trace, 1 for graph trace, and as you can see, it's already put the point 0, 2 over there. Now, sometimes when you try this, it might go, for example, on, let's say, 1.8 as a quick example. If that does happen, simply press the 0 button. It'll ask you x equals 0. Press enter. You'll snap straight to 0, the point where x equals 0, which is 0, 2. Press enter again, and it will give you the coordinates, and it will place it over there. You then press escape to get out of the trace mode. Okay, so there we go. We've now got the y-intercept and turning point labeled over there. Of course, I can change the color of the point to be orange along in conjunction with the graph as well. Okay, so that's what the graph looks like. And we've done all the different features. We've placed them on the graph as requested. Okay, so moving on to the final part of the session, we're going to look at rational functions. So rational functions have the form fx over g of x. So it's a ratio between the two functions. Now, in general, vertical asymptotes of these functions will occur when the denominator is equal to 0, as we saw back in reciprocal functions. However, there are exceptions that will apply when fx and gx have common roots. Now, what I mean by that is fx and gx, sometimes when you factorize those two functions, they will share a common function, a common factor, sorry. And when they share a common factor, those functions will share a common root. Now, what that means is that they will cancel out, and the graph will be the graph of that ratio without those two factors there. However, the root corresponding to those factors will end up in what we call a point of discontinuity, or colloquially we might call it a hole. You'll literally see a hole in the graph. Okay, so those don't happen very often, but when they do, it's something to be careful of. Finally, we can use the expand command to expand the ratio there, and henceforth obtain the equations of any oblique asymptotes that we might get. Okay, so what I've got over here is basically a graphs page that's showing you how some of the more basic rational functions work. So what I've got is 1 over x. Let me just quickly fix that. There you go. So I've got y equals 1 over x over here. And I want you to pay special attention to the x-axis here, which is y equals 0. It's a dotted line over there. When I change a to equal 1, what I've got is I've added x to it, or in other words, 1x. So if you add x and 1 and x together, what I'd like you to imagine is this x-axis, which is horizontal at the moment, it rotates 45 degrees anti-clockwise and pushes that rectangular hyperbola upwards, and something similar is happening with the bottom part over here. So that is the reason why the graph looks the way it is. It's just additional ordinates happening over there. Of course, I can change the gradient of the line to m equals 2, and I get y equals 2x plus 1 over x. Okay, let's change that back to 1. Okay, well, what happens if I want to change that x to an x squared? Okay, well, this is what's going on, m equals 2. So when m equals 2, I've got y equals x squared plus 1 over x, and something similar is happening. I've got the red graph, which is a parabola, and I've got the black graph, which is a rectangular hyperbola. And when you add the ordinates for that, you end up with this blue graph over here. So for positive x values, you can see that we always have positive y values for the final graph. However, for negative x values, what's happening is that the parabola is positive, but the rectangular hyperbola is negative. So there's kind of like a tug of war happening between the parabola's y values and the rectangular hyperbola's y values in terms of which part of the final blue graph it creates. Okay, so let's change that back to that. Now, what happens if you want to add a line and a truncus together? Well, you get something similar happen there as well. So I've got x plus 1 on x squared. So the red line is, of course, y equals x, and the black graph is a truncus. Okay, so of course I can then change the dilation factor for the truncus. I can change n equals 2 there. I can even increase the gradient of the line. And the last one I do want to show you is x squared plus 1 on x squared. So here we've got a parabola and a truncus that are being added together to create those two sections of the graph. You can, of course, also do things like make x squared minus 1 on x squared, which ends up looking like this. So this file will be made available to you at the conclusion of the webinar, along with the student worksheet. And this file will be made available to you, so you can actually play around with this and draw your own graphs. Okay, so let's go to the final part, which is an exam question for this function f of x. So to do a couple of things, we have to find and label asymptotes, find axis-intercepts, find stationary points to 2 decimal places, and then also find coordinates of the point of inflection. There's only a single point of inflection, and there's multiple stationary points. Okay, so first things first, let's try and define this. So f, open bracket x, close bracket, control define. Now let's get our fraction, x cubed tab minus 5, tab x squared minus x minus 2. Okay, so I've got that as it is. Okay, so what I'd like to do now is to factorize the numerator and denominator separately. So menu 3 for algebra, 2 for factor, and I want to extract the numerator. So to extract the numerator, I'm going to choose menu 2 for number, and then 7 for fraction, menu 2 for number, 7 for fraction tools, and then 2 for get numerator, and then f of x. Okay, I'll just put a comma x over that. So as you can see, this is what it factorizes to. It's basically the difference of cubes formula. X minus the cube root of 5, and then an irreducible quadratic on the right. Now let's factorize the denominator. Menu 3, 2, and then menu 2, 7, and 3. So get denominator, f of x, and I want to factorize that over all the reals. Okay, so the denominator, of course, factorizes nice and easily to x minus 2, x plus 1. As you can see, the numerator and denominator do not share any factors in common, and therefore we're not going to get any points of discontinuity that look like holes. Okay, however, we are going to get some vertical asymptotes. Let's go and find them. So the vertical asymptotes will happen when the denominator equals 0. So menu 3, 1 for solve, and copy and paste that. The denominator equals 0, comma x, and there we go. So we get 2 vertical asymptotes at -1 or 2. Okay, so now let's go and find any oblique asymptotes. So like I said in the page previously, we're going to use the expand command. So menu 3 for algebra, 3 for expand, and simply type in g of x. So g bracket x and enter. And it's f of x, my bad. There we go, let's change that to f of x. Awesome. Okay, so as you can see, f of x, when you expand it, it's basically the sum of the linear, which is x plus 1, and also the sum of 2 rectangular hyperbolas. So as x approaches infinity or negative infinity, these 2 fractions will basically diminish down to effectively 0, and therefore the function will behave like x plus 1. In other words, the oblique asymptote will be y equals x plus 1. Okay, so before we use calculus, I'm just going to go and graph this function. Okay, so as I'm going to graph this function, you'll notice that I've already got this page set up with axes from -6 to 7, -10 to 10, and I've got grid lines as well. So why did I do this? Well, if this was on an exam paper or a SAT paper, in most typical cases, you'll be given a graph axis and you'll be given the scale as well. You can use that to change your window settings. So to change your window setting, just menu 4 and 1. That will change your window settings. And of course, you can see X min, X max, and the scale, and ymin, ymax, and the scale is there as well. But then you might be asking as well, every time you've drawn a graph, you've never seen a grid over there. Okay, well, how do you get a grid? You simply right-click or control menu, go to hide, well, right-click control menu, go to hide show, and option 2 would be to show grid. And that will show you a grid over there, which is really good because when you draw the graph, you can then look at the paper that you have, and then it will be very easy to transform or translate the graph from your handheld over to the paper. Okay, so I'm going to just press tab and now type in f of x. So f, open bracket x, close bracket, enter. Okay, so there is what our graph looks like. Let's now, I'll just get rid of that so we can save some space. Let's draw the asymptotes that we saw before. So menu, graph entry, and relation, x equals -1 was our first asymptote. Press tab, x equals 2 was our other vertical asymptote. Let's change the color. Let's change that to pink. And change the color, or magenta rather. Okay, so x equals -1 and x equals 2. Let's change those to look dashed. There we go, change the attribute of that. This attribute will also be dashed. Awesome, and we've got the equations as well. Okay, so now let's type in our oblique asymptote. You don't need to use the function entry for this. You can actually do it straight into the relation entry line. Y equals x plus 1, and there we go. And we even got the equation there as well. It's pretty awesome. So let's right-click this one, change the color to pink, and change the attributes over to dashed. Okay, so we've now got all the various asymptotes drawn on the graph. Now let's go and find all the axes intercepts. Okay, so to find axes intercepts, I'm simply going to solve menu 3.1. F of x is equal to 0 for x. Okay, so that will give us x equals the cube root of 5. So that is our x-intercept, which you can see right there. So how do you draw that on the graph? Menu 6 for analyze and 1 for 0. It's going to ask you which graph because there's multiple graphs over here. I'm going to click, of course, the main graph here. Lower bound, click somewhere to the left. Upper bound, click somewhere to the right. And there we go. So that's the approximate value for cube root 5. Now we want it only to 2 decimal places. So you hover over that and simply press the minus button. So as you can see, my minus button is pressed over there. So when you hover over a number on the graphs page and you press plus or minus, that will increase or decrease the number of decimal places respectively. So that is the x-intercept. Okay, now let's go and find the y-intercept. That will just be f of 0, which is 5 over 2, which will show us 2.5 on the graph. So how do you do that? Well, menu, 5 for trace, 1 for graph trace, press 0 to go to 0, and there we go, 0, 2.5. Okay, so we've got our axes intercepts, we've got our asymptotes. The last thing to do is to get the coordinates of the turning points. Okay, so to get the coordinates of the turning points, I'm simply going to solve the derivative is equal to 0. Okay, so what I might do is just quickly find the first derivative of f of x. There we go, and let's solve that equal to 0. Menu 3.1, so that equals 0 for x, and there we go. So we get a single negative x value, and we get a single positive x value. So let's go and place them on the graph over here, because the y values we can get on the calculator page, but the graphs page does that for us as well. So menu, analyze minimum. Let's choose this part over here, left, right, and there we go. So I'll just reduce the number of decimal places. That should be 3.07, and here should be 5.5. There we go. So there is our local minimum, and our local maximum should happen at negative 2.45. So menu, analyze maximum, choose this graph here, left, right, and there we go. So let's just reduce the number of decimal places, neg 2.45, reduce the number of decimal places, neg 3.05. Okay, so we've got our 2 stationary points. Now let's finally finish off with the with the point of inflection. So I'm simply going to go to menu 3.1. To get the second derivative, I'm going to press the template button. And then as you can see, I've got a d2 over here. So press that, and there we go, d2 dx squared. And in here, I'm just going to type in f of x. And we want to equate that to 0 for us to point of inflection, comma x, enter, and there we go. So that's the exact value. The approximate value is about 0.67. Okay, so of course, We do have to do more tests to ensure that it is indeed a point of inflection, but the graph shows that to us already. 0.67 is about here, and that certainly looks like it's a point of change of concavity. Okay, so we're going to go to Menu, Analyze, and then Inflection, choose the graph, go somewhere left, somewhere right, and as we said before, 0.67 is where we're going to have our inflection point. 0.67, actually get 2.12. There we go. Okay, so as you can see, it's getting a bit crowded over there, but we've got all the information we require to accurately draw this graph on our papers. Okay, so that is all we have time for today. As you might have seen, I've done all this on computer software. Now, if you would like to do the same sort of analysis using your computer software, I would like to draw your attention to the fact that with the current remote learning situation, Texas Instruments is making the software license available for free for a free 6-month subscription. And all you got to do is go to the website. There will be a link to this website in the chat box. So please check that out if you're interested in getting the software.